Thank you everybody for coming out too. We need to get the word out about climate change, and I have a lot to tell you, and at the end of this you're all going to be certified climate scientists, so you need to go out, spread the word. My name is Fletcher. I'm a professor of geology and geophysics, and I'm an associate dean of academic affairs at the School of Ocean and Earth Science and Technology at Mānoa. What you really need to know is that I'm a geologist, and I've been connected with the Earth since early days. In grade school, at that point I started my long, not proud career of doing poorly in classes, and it's because I'd much rather be outside studying nature as she presented herself to me. I did manage to accumulate a few degrees along the way, but fundamentally I'm an environmentalist, an ecologist, a geologist, and I'm very distressed about climate change, and so I feel that it's critically important that we spread the word on how dangerous climate change actually is. So let's look at the data from NASA. This begins in 1880. This is a counting down through time up to present day. We're in the 1950s and 60s and 70s. There are several characteristics you can see here. One is that no place consistently warms year after year. The entire surface of the planet does not warm year after year. So there is spatial variability from one place to another, and there is temporal or time variability from one year to the next. Climate change is a highly variable process, and that makes it very difficult to study. This is the same database averaged down to one global average temperature at Earth's surface, taking into account the temperature on land and the temperature in the oceans. And you can see it's very variable. We have cold years, which tend to be La Niña years. A La Niña is where the trade winds in the Pacific blow strongly and tend to bury heat in the ocean in the western tropical Pacific. And that heat comes out of the atmosphere and it is stored in the shallow ocean. These warm years tend to be El Nino years. We're going to spend some time talking about El Nino. El Nino is when all that water that is warm in the western tropical Pacific surges across the Pacific to the east and releases its heat to the atmosphere, and you get a record-setting warm year. You can see the overall trend. There is a period of quasi-stability prior to World War II. Then things took off at World War II. There was another period of quasi-stability, but it was a step up from pre-World War II. And then in the late 1970s, global warming really took off. There are several ideas as to why that might be. One might be because we've passed the first of 9 Clean Air Acts, which cleaned up smokestack emissions and were emulated in Europe and other industrial nations, so that the amount of soot that we were putting up into the atmosphere decreased. That soot was reflecting sunlight out before it could reach Earth's surface. So we cooled the planet up until the late 1970s. The Clean Air Act then made the air cleaner to breathe and more healthy, but it may have triggered this acceleration in global warming. 2014 was a record-setting year, followed by 2015, which was a record-setting year, and then 2016 was a record-setting year as well. And now 2017, as of the end of June, is coming in as the second hottest year on record. So it may not be record-setting, but it is close. So what is causing anthropogenic climate change? Anthropogenic simply means human-made, and it boils down to an enhanced greenhouse effect. The greenhouse effect is a natural process that keeps the temperature on Earth's surface on the order of 30 degrees Fahrenheit warmer than it would be otherwise. If we did not have a natural greenhouse effect, the average temperature would be several degrees below freezing, and life as we know it really wouldn't exist on Earth. And the greenhouse effect simply is that there are a set of gases in the lowest layer of the atmosphere, known as the troposphere, and these gases will trap heat. And you all know that when the sun shines down onto the parking lot warms up, and that heat re-radiates off. That's infrared radiation, and these gases are opaque to infrared radiation. They trap infrared radiation, just like you throw an extra blanket on your bed when it's a little colder. It builds up heat and prevents it from escaping from Earth's surface. Above the troposphere is a higher level in the atmosphere called the stratosphere, and we'll look at how that's responding to global warming in a second. So globally, the greenhouse gases, and I know this is hard for you guys to see in the back, consist of carbon dioxide, and this is 65% of our greenhouse gas emissions are carbon dioxide from fossil fuels, and then another 11% of carbon dioxide from deforestation and mixing soil up so that it mixes with the air. Then we have methane, nitrous oxide, and chlorofluorocarbons, the fluorinated gases. The insidious thing about carbon dioxide is that once you put it up into the atmosphere, as soon as you turn your car on, about half of it will stay there for centuries, and in fact, even up to over 1,000 years. These other gases, methane and nitrous oxide, have shorter residence times in the atmosphere. But carbon dioxide is essentially causing permanent climate change on a human timescale. Once you trap some heat in the atmosphere with these gases, the warmer air holds more water vapor. And water vapor is actually the most powerful greenhouse gas, except it cycles through the atmosphere within a week or two, right? The water cycle, we all know about the water cycle. But if you create long-term warming to the atmosphere, you will create a long-term increase in the amount of water vapor. So for every degree of warming caused by these gases, the feedback effect of more water vapor gives you a second degree of warming. So you get 2 for the price of 1. These feedback effects are very important. In the United States, our carbon dioxide comes from electricity, transportation, industry, residential and commercial energy, and other types of non-fossil fuel combustion. Methane comes from fracking, from landfills, and from feeding cows corn. Grass-fed beef is natural. Cows that are fed corn get fatter, faster, and there are now 1.5 billion cows on this planet because the human population demands beef. But in order to grow these cattle fast enough, we feed them an unnatural food, and that upsets their digestive system, and they're producing methane out of both ends, and it is a very significant source of methane. They say one of the things that any one person can do is to switch over to a more plant-based diet with regard to helping the climate change problem. Nitrous oxide comes largely from fertilizing soil because plants need nitrogen. They're nitrogen limited, so we feed them more nitrogen. And the fluorinated gases are used as coolants, and they trap heat and stay in the atmosphere for a long time. So here's the temperature change of the troposphere. That's the layer of air we live in. It's about 6 miles high from Earth's surface. You can see all the red means that it's been gaining heat. This is in degrees centigrade per decade. So this dark red is about 0.4 degrees centigrade per decade. And this is the trend since 1980. If we're trapping heat here close to the Earth's surface, what's happening to the stratosphere above us? Anybody want to be brave and take a guess? What's happening to the stratosphere above the troposphere if we're building up heat in the troposphere?
It's also trapping heat?
It's not also trapping heat. It's getting colder because we're keeping that heat here. So satellite measurements of the stratosphere show that it's been cooling over the same time that the troposphere has been warming. So this is one of our proofs of climate change for those who are interested in knowing what the proofs are. And of course, we all are. The carbon dioxide comes out of largely our industrial emissions. We are treating the atmosphere like an open sewer. We finally have some laws in place to regulate greenhouse gas emissions and to regulate the amount of pollutants that we are putting in the atmosphere. The atmosphere is really a very thin environment. The troposphere, this layer that we live in, is just that little pale orange layer, and the rest of the atmosphere is 100 miles high. The troposphere is only 6 miles high. So that's where all our pollutants are being held. Deforesting large portions of the planet also contributes to the increase of greenhouse gases because we don't have those trees to store the carbon. And this is concentrated animal feeding operations where we are feeding cattle inappropriate diets, and they are producing methane, which is 25 times stronger than carbon dioxide as a heat-trapping compound.
Hi, this is Bill Putman. I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural land and ocean reservoirs. In the Northern Hemisphere, we see the highest concentrations are focused around major emission sources over North America, Europe, and Asia. Notice how the gas doesn't stay in one place. The dispersion of carbon dioxide is controlled by the large-scale weather patterns within the global circulation. During spring and summer in the Northern Hemisphere, plants absorb a substantial amount of carbon dioxide through photosynthesis, thus removing some of the gas from the atmosphere. We see this change in the model as the red and purple colors start to fade. Meanwhile, in the Southern Hemisphere, we see the release of another pollutant, carbon monoxide. This is a gas that's both harmful to the environment and to humans. During the summer months, plumes of carbon monoxide stream from fires in Africa, South America, and Australia, contributing to high concentrations in the atmosphere. Notice how these emissions are also transported by winds to other parts of the world. As summer transitions to fall and plant photosynthesis decreases, carbon dioxide begins to accumulate in the atmosphere. Although this change is expected, we're seeing higher concentrations of carbon dioxide accumulate in the atmosphere each year. This is contributing to the long-term trend of rising global temperatures. The Orbiting Carbon Observatory 2, or OCO2, will be the first NASA satellite mission to provide a global view of carbon dioxide. OCO2 observations and atmospheric models like GEOS 5 will work closely together to better understand both human emissions and natural fluxes of carbon dioxide. This will help guide climate models toward more reliable predictions of future conditions across the globe.
Modeling these processes is important if we hope to manage them. And these models get down to a very fine scale, individual tracts of forests, individual coal-powered electricity plants. That's how we know how to scale our policies and our laws so that they can be most effective in mitigating this problem. There is such a thing as natural climate change. And most of the information about natural climate change that we have has come from coring ice in Greenland and Antarctica, as well as mountain glaciers. This is a drill in Antarctica. This is the drill room. These are very sophisticated and advanced scientific initiatives funded by the National Science Foundation involving teams of scientists. Here you can see a drill run by the Russians, Vostok Ice Core. It's cored through 2.2 miles of ice in Antarctica. 2.2 miles of ice gets you almost 1 million years of history. And the way this ice accumulates is year after year, snow falls, and it gets buried under subsequent years of snowfall, and the openings, the pukas in that snow trap bubbles of air, and that air is a little sample of the atmosphere. And as you drill down through the ice, you can sample ancient atmosphere that is fossilized in this ice. This is a storage room where these ice cores are stored for later analysis. Here is a sample of the ice in a vacuum cylinder being melted to release the gases from the air bubbles in there and to measure not only carbon dioxide, but methane and all sorts of other types of gases. And this very busy looking diagram is the result. What we have here is time on the bottom axis. This is 400,000 years ago up to present day. And in green is the history of carbon dioxide. And in purple is the temperature. And because the air is so well mixed on our planet that carbon dioxide in Antarctica can be strongly interpreted for carbon dioxide worldwide, and the temperature in Antarctica can be interpreted for the temperature worldwide. You may notice that there are these low points. These are ice ages. So as we come from 400,000 years ago, we have an ice age, another one, and another one. And in between each of these ice ages, we have what are known as interglacials. So we go ice age, warm period, ice age, warm period. This regular rhythm to Earth's climate is controlled by how Earth changes its orientation to the sun. We'll go into that in just a second. We live in the most recent interglacial, known as the Holocene, or recent time. It began on the order of 10,000 years ago. And our species was ready to move on from hunter-gatherer culture to agriculture, domestication of animals, living in communities that were dedicated to farming. And the first cities and the first communities began 8,000 years ago, 5,000 years ago. And with that, the deforestation of the planet began, the domestication of animals that produce methane, and there's a very strong hypothesis that actually humans took over climate change as early as 8,000 years ago and 5,000 years ago. Rather than just 100 or more years ago. These interglacial cycles last about 100,000 years. So roughly every 100,000 years, we have paleoclimate changing. And this is because of what are known as Milankovitch cycles. Milutin Milankovitch was a mathematician who was a prisoner of war in World War I. And while he was a prisoner of war, he worked out the mathematics of the gravitational influence of all the planets on Earth. And he calculated for us that Earth goes from a more circular orbit around the sun to a more elliptical orbit around the sun every 100,000 years and every 400,000 years. And Earth's axis tilts more towards the sun and less towards the sun every 41,000 years. And that axis wobbles or draws a circle in the sky every 26,000 years. And the reason this is important is because sunlight reaching the Arctic will control whether or not snow melts in the summer. And if the snow melts, then there's no increase in what's known as the albedo, or the reflectivity of the Arctic. But if some snow won't melt, decades, century, millennia after millennia, you spread this white surface across the Arctic and you reflect more sunlight. And as you reflect sunlight, you cool the planet. So what we have here is another feedback. We have the orbital parameters, which may tilt a little bit away from the sun. That allows snow from one winter to last until the following winter. That spreading reflectivity, or albedo, reflects more and more sunlight out. And so the orbital parameters start you down the road to an ice age, and the feedback, the spreading albedo, takes you all the way down into an ice age. And then these orbital parameters will tilt a little bit more towards the sun, and snow melts during the course of the summer. That brings you part of the way up, and the feedback of melting all that snow and reducing the reflectivity takes you the rest of the way. And if you notice, it's not a perfect 100,000 years. Buried in here are 100,000 year, 400,000 year, 21,000, 26,000 year, and 41,000 year cycles. All this noise is like sheet music, and it's the amount of sunlight and the feedbacks hitting the northern hemisphere at about 65 degrees north latitude. And so we can predict the amount of sunlight going back in time. That's 500,000 years. There's 1,000,000 years. And going forward. That's 500,000 years in the forward and 1,000,000 years in the future. And we should be heading down into our next ice age. We'll get to that in a minute. So what are the consequences of global warming that are dangerous for humans? And at this stage, let me take a break. Are there any questions? Does anybody have any comments? Want something clarified? Yes?
You mentioned more water vapor in the atmosphere with the warming Earth. And I've heard it said once that maybe that could be kind of a homeostasis effect of the Earth, where if you put more clouds in the sky, you're going to get more reflection.
Right.
To slow down that process.
Right. So if there's more water vapor in the atmosphere, does it produce more clouds? And clouds can have a couple of effects. Not every cloud has a clear-cut climate effect. It turns out that high-altitude cirrus clouds, which are made of small ice particles, will actually trap heat that is trying to escape to space. And in fact, there's a geoengineering approach, which would be to destroy these clouds and let that heat escape to space. Whereas lower clouds are capable of reflecting sunlight, and that would have a cooling effect. Very simply, if you look at the summertime when conditions are hotter, it's not any cloudier than in the wintertime when conditions are cooler. So that very simple seasonal experiment suggests that we're not going to see an increase in cloudiness as a result of building up the water vapor. But cloud research is one of the more difficult aspects of this. The papers that have been published in the last 5 years or so are all suggesting that the clouds are going to respond to warming by causing more warming rather than less warming. All right, so here's where we will focus in a little bit more on a more recent geologic time scale. Here is 24 and 20,000 years ago. This was the depth of the last ice age. The orbital parameters changed. The feedback effect took hold, and we moved out of the last ice age and into the current interglacial. The orbital parameters were at their maximum warming configuration around 12,000 years ago. And from 12,000 years ago, the orbital parameters started pushing us towards the next ice age. And in fact, temperature has fallen on the order of 1 degree over the last 12,000 years. And we are heading into our next ice age if we hadn't done that. We have taken over Earth's climate, and it's now been calculated that we are going to skip the next ice age. Humans have performed an enormous geophysical experiment. We have overcome the gravitational influence of the solar system in driving climate cycles. And we are now forming our own climate. We have now warmed the planet, the Earth's surface, about 1 degree C. That's a little less than 2 degrees Fahrenheit. This has led to a rise in heat waves, which I will explain to you, an increase in intense rainfall because we have more water vapor, and it has started melting glaciers and swelling the oceans with more heat, so we have a rise in sea level. We hope to stop global warming at 2 degrees C, and in fact there was a global treaty signed in Paris in 2015 under the auspices of the United Nations, and it is aspirational to actually stop it at 1.5 degrees C. The limitations in greenhouse gas emissions that all the nations signed on to will actually send us past 2 degrees C, and we won't stop warming until 3 degrees C. So we need to continue to meet under the United Nations and ratchet down our commitments so that we emit fewer and fewer greenhouse gas emissions. At 3 degrees C, large regions of the planet become too hot to support life. The Middle East, North Africa, portions of Southern Europe around the Mediterranean, large parts of Central America, India, Southeast Asia. These areas will see drought, which will lead to famine. We'll see decreases in freshwater availability. And in fact, we are seeing this already. This paper came out in Proceedings of the National Academy of Sciences. It says, Climate Change in the Fertile Crescent and Implications of the Recent Syrian Drought. Worst drought in the instrumental record, causing widespread crop failure and a mass migration of farming families into urban centers in Syria. This occurred from 2007 to 2010. As these families moved into Aleppo and other Syrian cities, they found a lack of medical, food availability, a lack of jobs, a lack of housing, a lack of electricity, a lack of fresh water. And they also noticed that their president, Bashar Assad, was jetting around the world, spending a lot of money, living the high life, and here they were suffering in these cities. This drought and the movement of these farmers into the cities had a catalytic effect, contributing to political unrest. This is a Syrian refugee camp. There are millions of people attempting to flee the civil war that developed in Syria against the president. That civil war opened up for ISIS to come in and for Al-Qaeda to come in. It became a very chaotic area and still is, and people fled. This is a United Nations refugee camp, and there are several of them in northern Syria, but people are moving beyond the refugee camps. They are in fact migrating out of the Middle East, away from the Syrian conflict. And that drought didn't confine itself just to Syria. The Middle East and North Africa experienced this drought, and food became a severe problem. There are two general pathways of migration, either up through Turkey and the Aegean Sea or into North Africa, where Syrians and others were joined by North African immigrants attempting to leave from Libya, which now has no government, and so you can go through there. As this wave of humanity moved into Europe, it caused a huge, profound effect. What do you do with hundreds of thousands of people attempting to move into your country? Coming out of Libya, you have crowded boats. You can't see it, but there's a whole layer of people underneath these folks. Right here is an opening in the deck, and there's another layer of people underneath the ones that are in the open deck. Typically, the smugglers take these boats out to 3 miles offshore of Libya. They pull the engine and they go back in, and they hope that the Italian Navy or some other country will rescue these boats. These boats are not seaworthy. They often collapse. There are photos of these boats tipping over. This one is running out of air, and I count 4 life preservers in there. A lot of these people do not know how to swim, and so we have horrible instances of tragedy taking place. Perhaps you recall the little boy that washed up on a beach, that photo from last year. Here we have the Italian forces ignored a sinking ship full of Syrian refugees and let more than 250 people drown. As these people move into Europe, the rise of nationalists and populists in the political spectrum in these countries starts to dominate the polls. You have the immigration of refugees arising from this complex set of circumstances, among which is climate change, leads to reaction of local populations who see their way of life, their values, and their culture threatened by these incomers. You have the rise of ultra-conservative, ultra-right parties going by the terms populism, nationalism, the Freedom Party, the ultra-right-wing movements. These are led by demagogues. These are politicians who tell you the reason you don't have a job is because those folks are taking your job from you. They are threatening your way of life. They're threatening your culture. Elect me and I'll protect you. Right-wing parties in France, the Netherlands, Germany, England, Denmark, the US, and others have called for a ban on Muslims. Brexit was driven by anti-immigrant rhetoric of the UK Independent Party, and President Trump rose to power on the promise to build a wall on our southern border, restore jobs, and return to traditional values. So we're seeing all across the Northern Hemisphere this political reaction. It goes back to a drought that the climate models show is related to climate change. This is what human migration looks like. So large regions too hot to support life, that's what it looks like. At 4 degrees C, if we keep going, we will lower the surface of the Greenland ice sheet and the Antarctic ice sheet to the point that it becomes a self-fulfilling prophecy. Once you start to lower the ice sheet, you're into higher probability of warm air, higher probability of rain, lower probability of snow. You move past the tipping point and you start to you move into the unstoppable melting of these ice sheets, potentially leading to hundreds of feet of sea level rise, which will displace more human populations, which will lead to more climate refugees. At 6 degrees C, potentially every other breath you take will not be produced by the phytoplankton in the ocean that engage in photosynthesis. Our air is given to us by algae in the ocean. And when we bake them out of existence by raising the ocean temperature several degrees, they stop being able to metabolize and we don't see photosynthesis taking place. So when someone says to you that climate change is an existential issue, I hope you take it seriously, because at its very worst, it is an existential issue. And business as usual, that is, if we keep on releasing greenhouse gases as we have, will take us to 4 to 5 degrees by the end of this century. Climate change is also causing severe weather. In 2016, West Virginia experienced 1 in 1,000 year flooding. In Texas, there were 3 major flash floods, each of which broke 1 in 100 year flooding. In 2016, we had over 3,800 wildfires burning over 110,000 acres just in California. In the American Southwest, we had air temperatures at 120 degrees. So our internal core temperature is in the upper 90s, and when the air temperature is in the upper 90s, your bodies can't offload heat. That leads to heat stroke. And if there's humidity in the air, which there will be because warm air holds more moisture, you get a thin layer of moisture on your skin, at which point heat stroke doesn't have to start at 98 degrees, it can start at 90 degrees because that layer of moisture on your skin will trap heat instead of allowing it out of your body. So at 90 degrees, you can begin to affect the human health. And if you have to go outside to grow food. You have to go outside to build buildings. We need to be outside and able to work outside. But if the temperature is so high that you can't do that, you can't live in an area. In the summer of 2016, New England had its hottest summer ever. And in the winter of 2016, it had its single largest snowstorm ever, Snowstorm Jonas. So how do you get record-setting cold temperatures and record-setting snowstorms if we're talking about global warming? We'll explain that in a second. So overall, 2016 was the second hottest year on record in the United States. It was the second most expensive year for disasters. 15 disasters, over $1 billion in damage, for a total of $45 billion in weather disasters in the US. And this is Mississippi, one of those disasters, a 1 in a 1,000-year event, where 100,000 people went homeless because of flooding. Within the space of a week, officials realized we have 100,000 people that need taking care of. Local governments are not prepared for that. No one plans to take care of 100,000 people. The pregnancies, the diabetes, the elderly, the babies, the sewage needs, the fresh water needs, the food needs, all the other diseases. In 100,000 people, you have the entire arc of human diseases and needs. And within 1 week or 2 weeks, it suddenly needs addressing now. These disasters lead to internal migration. People leave an area, they'll move to where relatives are in other cities, or they will just go to other cities and they won't come back to these areas. So you see migration of people even within a nation occurring. We want to downsize government, right? That's the mantra, small government, small government. But who's going to take care of you when this sort of a disaster hits? It's going to be government that takes care of you, or non-governmental groups that step up and plan for it. But this takes money, and it takes all of us realizing that these sorts of disasters are on the rise. Well, these disasters take place because of what's known as Arctic amplification. So here is our typical Arctic, reflecting sunlight off to space, and that reflected light doesn't do any warming. But as Arctic sea ice shrinks and the snow cover shrinks, you have dark area exposed, which absorbs sunlight, warms up, and releases infrared radiation, as we've talked about. So this leads to the Arctic being 5 degrees Fahrenheit warmer than the global average. The rate of warming at this point has led to the Arctic warming 5 degrees more than the rate of warming for the rest of the planet. This is called Arctic amplification. Now, most of the sunlight hits at the equator, and air currents and ocean currents will export that heat towards the poles. As air currents move heat from the equator towards the North Pole, these air currents will turn to the right because of the Coriolis force, and they will form 2 rivers of air, one of which is the polar jet stream. And the polar jet stream, you're looking down on the North Pole as we turn the planet. The polar jet stream is this rainbow color. And as the Arctic warms faster than the equator, the gradient, the temperature gradient decreases, and the jet stream slows down, and you develop these big meanders. And a big meander like that one will pull Arctic air down, and you'll get record-setting snowfall. And a big meander like that one will pull tropical air up, and you'll get a record-setting heat wave. And these meanders walk across Europe and Siberia and North America very slowly, so the heat wave takes a couple of weeks to make its way across the United States, or the snowstorm takes a couple of weeks. It's all because of global warming. And here is a typical temperature map in July. And notice that there's cold, hot, cold, hot. This patchiness to temperature is because of these large meanders in the jet stream. Pulling heat up from the south gives you a heat wave. Pulling air down from the Arctic gives you a cold snap. So you get extreme weather events. In 2003, Europe experienced a lingering heat wave. You can look this up on Wikipedia. It has its own page. 70,000 people died. The way people die in a heat wave is everybody runs their air conditioning. That causes a blackout. And when you live in the upper floors of an apartment building, You can't get water because that takes an electric pump. You can't open your windows. There's no air conditioning, and you can't go up and down the elevator. And if you're elderly and you don't have a support network, you don't have a family, and you live alone, and if you're ill or if you're extremely young, you can't take those 27 flights of stairs, and you get trapped in your hot box, and within 72 hours, serious medical issues begin to develop. You can call for help, but at that stage, everybody in the city is calling a few thousand police, a few hundred ambulances. No one takes your call, or if they do, they say, "You're on our list, we'll be there in 2 weeks." So this is how heat waves lead to fatalities. We had one in Russia, 55,000 deaths in 2010. Now, every single year, there are heat waves that kill thousands of people someplace on the planet. These are becoming a major characteristic of climate change. So extreme weather, global drought has increased 10%. Global extreme rainfall has increased 12%. The record hot days outnumber record cold days by 12 to 1. In an unchanging climate, that would be 1 to 1. 9 of the 10 deadliest heat waves in history have occurred in the last 17 years, just since the year 2000. And about a year ago, maybe 2 years ago, Munich Re, a major insurance company, announced that someplace on the planet we're having almost one weather-related disaster a day. 335 weather-related disasters. This is twice as many as 20 years ago. And this is Munich Re data from 1980 up to 2014. These are loss events recorded by that insurance company, geophysical events, tsunamis and earthquakes leading to loss in red, meteorological events such as storms. In light green and dark green are hydrological events such as floods and mass movement. And in orange are climatological events such as heat waves, drought, and forest fire. And you can see overall there's been this strong increase in loss events as measured by insurance companies over the last couple of decades. Does Hawaii experience extreme weather? Well, we just went through an El Nino. And let's remind ourselves of what an El Nino is. So our normal weather system is we have trade winds, they blow water to the west, and this is the West Pacific warm pool. A La Nina is when the trade winds are very strong, and we get a big West Pacific warm pool. Lots of water over here. It's warm, it absorbs heat from the atmosphere. Sea level is high. The atmosphere cools in a La Nina, and with all that warm water, it evaporates easily and you get flooding. You get extreme flooding, and in 2010, we had extreme flooding in Australia. Extreme flooding in Southeast Asia causes food spikes, food prices to spike because you flood out the rice agriculture. So there's our normal situation. That was a La Nina I explained, and an El Nino is where the trade winds fail. The West Pacific warm pool surges across the Pacific. This area is replaced with cool water from below. You get drought. That also leads to spikes in global food prices. As this water moves south of Hawaii, it's warm. It warms up the ocean around Hawaii. You get coral bleaching. It evaporates very readily, so we get extreme rainfall. It brings heat, so we get extremely hot days. And over here, you get flooding throughout the American Southwest and Latin America and South America. This warm water also fuels tropical cyclones. Our hurricanes come from this part of the Pacific, and the fuel for those hurricanes comes from ocean water. So let's look at all of this. So the El Nino of 2015, 2016, this is Dillingham Boulevard in downtown Honolulu. This is what sea level rise looks like. Rain normally goes into the gutter and down a drain into a pipe and out to the ocean. It's called our drainage system. But as sea level rises, salt water goes up into that drainage system and blocks it, so that when you get extreme rain, it has nowhere to go, and you get flash flooding taking place. We had 11 days of record-setting rainfall in Honolulu during that El Nino. We had 24 days of record-setting heat, and HECO, our energy utility, set out emergency bulletins to please do not run your air conditioning all night long because they saw a blackout coming. And it didn't happen, thank goodness, but everybody, no trade winds, everybody closes the windows and runs their AC. That can bring down the grid. We had 9 months of drought in that El Nino, 15 tropical cyclones. The previous record was 11, and for the first time in history, Hawaii was surrounded by 3 named hurricanes at the same time. We were monitoring 3 hurricanes. That had never happened before. This paper says that there will be an increased frequency of extreme La Niña events under greenhouse warming, that ENSO-related catastrophic weather events are likely to occur more frequently with unabated greenhouse gas emissions. And this one came out this morning. Continued increase in extreme El Nino frequency long after 1.5 degrees C warming happens. If we stabilize at 1.5 degrees C, we will continue to see extreme El Ninos. In other words, as we warm the world, these extreme El Ninos are going to occur with more and more frequency. What we see in Hawaii during an extreme El Nino is heat waves, extreme rainfall, failure of the trade winds, active hurricane season, large winter waves. The Eddie Aikau surf contest was canceled twice in 2015, 2016, because the waves were too big. Drought, warm ocean temperatures, and of course, coral bleaching. All this happened in that recent El Nino. And now we find out that this is likely to occur more frequently. So that was a glimpse of our future. This is how Hawaii will be affected. All right, how does climate change affect Hawaiian ecosystems? A brilliant professor on the Mānoa campus named Camilo Mora published a paper in Nature in which he described the climate envelope. So we have 150 years of climate. You have warm years and cold years, but basically climate stays within an envelope. And ecosystems evolve into this envelope. Ecosystems can tolerate the warm years and can tolerate the cold years. But climate change pulls that climate system out of its envelope. That's our historical climate. As you leave the climate envelope, cold years become hotter than your previous heat waves. And your hot years become off the charts record setters. So leaving the climate envelope means that you are leaving behind the evolutionary foundation of your ecosystems. And our ecosystems are what give us our drinking water. Our trade winds come out of the northeast. They hit our shield volcanoes. They are forced to go up to higher elevation. In that cold air, they condense and they form our clouds. But you all know when you fly out or fly in from a Hawaiian island, you leave the clouds. So there's a top to our clouds and there's a bottom to our clouds. The top is called the trade wind inversion, and this process is called orographic or orography. So there's the base of the clouds. That base is a line where the rate of condensation exceeds the rate of evaporation. And there's the top of our clouds. These clouds give us our fresh water. They are the source of our drinking water. They are the source of our ecosystems. As we warm the air, that boundary between evaporation and condensation changes. And the base of our clouds can rise. And the top of our clouds can fall. So you get shallower clouds. Air now can flow right through these valleys and not condense, not produce clouds and not produce rain. On the slopes of Mauna Kea, the base of the clouds is migrating over 1 meter per year up the slopes. And the number of days where we get the tops of our clouds suppressed has gone from 80% of the days in the 1970s to 90% of the days now. And what's happening with the tops of our clouds is it's called the Hadley cell. There's air coming out of the equator, it goes up into the atmosphere, and then it comes back down, and that's what creates the tops of our clouds. And that air is accelerating, and our clouds are being suppressed downwards. So our clouds are getting shallower. Potentially related to this is a decline in rainfall. Here we have rainfall for the last roughly 80 to 90 years on the left arrow. So on the island of Kauai, over the last 80 to 90 years, there's been a 0.9% decrease in rainfall. But in the last 30 years, there's been a 3.6% decrease in rainfall. Statewide, in the last 30 years, we have a 6% decrease in rainfall. On the Big Island here, we have a 6% decrease in rainfall over the last 30 years. Over the last 80 to 90 years, it's much less. This means that there's an acceleration in rainfall decline in Hawaii. So rainfall has been declining slowly for 160 years, 160 years as best we can determine. This is the work of Tom Giambaluca and colleagues and students on the Manoa campus. Recent decades have been especially dry. This is strongly influenced by variability, meaning that El Nino and La Niña and some other variability processes strongly influence this. We can still get wet years and dry years, but there is this long-term decline. Kona has seen the most severe decreases in rainfall statewide. And as far as predicting the future, there are two types of models, and they don't fully agree. One is based on statistics. It says that we'll see small increases in wet windward areas. So Hilo, for instance, may see a small increase in rainfall and severe decreases in dry leeward areas, such as around Kona. Another type of model is based on the physical laws governing rainfall. So this is called physical modeling. Those models suggest that there'll be significant increases in windward areas and small decreases for leeward areas, so sort of the flip. But in either case, we see decreases in the region of Kona and some type of increase in the region of Hilo. So changes in rainfall. Our rain gathering and rain delivery systems, our infrastructure, are scaled to a certain type of rain. Rain is changing. We need to think about how do we change our rain infrastructure. We also have changes in wildfire. This is the work of Clay Trauernicht on the Big Island. This is area burned in thousands of acres from 1910. You can see there's a strong recent increase in the occurrence of wildfires. The occurrence of wildfires is a result of three factors. People. 99% of the fires in Hawaii are started by people, not by lightning. Lightning is a rather rare process in the Hawaiian Islands. Vegetation. 80% of the area burned is in expanding, alien, fire-prone grasslands and shrublands. So invasive species that are fire-prone and expanding areas characterized by drought, so expanding drought. And then climate is the third element. 75% of fires occur in drought conditions. This is a map of areas burned over 20 years. The dark red are burned areas. And so the probability of fire is shown here. There's a 15% probability of wildfire in these dark red areas. The yellow areas have more like a 5 to a little bit less than 10% probability of occurring with wildfire. Clay has modeled this based on current rainfall. His model predicts this probability of wildfire. This is very similar to the observations. And by mid-century, his model would have expanding wildfire areas, increasing probability of wildfire in some of these darker colored areas. So we have this model of wildfire here in the Kona region. This paper came out recently. It looked at over 900 species of plants and animals in the ocean, in terrestrial ecosystems, on land, in aquatic ecosystems. And it found that 47% of all plant and animal species are no longer found where we used to find them. They're no longer found in their historical footprint. This is called local extinction. It doesn't mean they've gone extinct off of the planet, but it means they've gone extinct where they traditionally existed. And when you live on an island, local extinction is permanent extinction. In California, you might have found something at the base of the Sierras, and now you have to go up 1,000 feet in elevation and you can find it there. But here in Hawaii, that's not the case. So we are experiencing planetary-wide local extinction. And unfortunately, coral reefs have very bad news as well. Between 1985 and 2012, the global percentage of coral reefs that bleached tripled in that 28-year period. And by mid-century, 98% of reefs will experience annual bleaching, which kills a reef. Now, some reefs on continents may be able to migrate up to colder waters, but on islands, that won't be the case. So our coral reefs, we're looking at the last few decades for our coral reefs. And bleaching is largely a function of increasing water temperature, but it's also a function of lowering pH. As the ocean absorbs carbon dioxide, the pH goes down. This is called ocean acidification. And we're already seeing pteropods. A pteropod is a polar plankton that is the base of the food chain for krill. And krill are the base of the food chain for salmon and for various types of whales and for other large marine animals. And the pteropods look like melted wax. The edges of their shells are corroded, they curl over, and this is because of the acidification of the oceans. These shells are made of calcium carbonate, CaCO3. Most of the plankton out there in the temperate and tropical waters are made of CaCO3, and some in the polar waters are made of CaCO3. Other types of plankton are made of silica or quartz. And of course, CaCO3, calcium carbonate, is what reefs are made of. It's what fish bones are made of. And the ability to secrete the skeletal components that you need is compromised with ocean acidification. And between warming the water and then acidifying the water, you go from an ecosystem in a reef that is robust. This is about 1 degree C of warming and 375 parts per million of carbon dioxide. We're now at 410 parts per million of carbon dioxide. Here we are at 450 parts per million of CO2, 2 degrees C of warming, which is what we get during an El Nino. Add to this that we fish out the herbivores. The herbivores are the only thing cropping back this algae. These invasive algae outcompete corals. If you put invasive algae and a coral on the same seafloor, the coral will lose every time. But fish that eat that algae, herbivores, allow that coral to potentially compete. But we overfish our reefs, many of them. And with warm water and overfishing and then dumping pollutants off of our watersheds, right? What are human waste and other elements that come out of our watershed? Nothing more than nutrients or plant food, allowing for the algae to bloom. And then the poisons that come out of our watersheds, you know, the unburnt gasoline out of our car, the cadmium and mercury that fall off your brake pads when you brake your car. All these things get gathered by rain. They're taken out into the shallow coastal ocean. And corals are animals, so they are poisoned, and we're seeing the rise of coral diseases like white band disease and black band disease. So corals are being suppressed and poisoned, and their partners, the fish, are disappearing, and invasive algae. And eventually you see the coral reef just collapse, and you have a sea of weeds and gravel.